Hello students, this is the continuation video on the chapter laws of motion. So watch the video till the end and note down these topics which I have noted down in my board in your exercise book, right? So what is an impulse? It is a measure of degree to which an external force produces a change in momentum of a body. Like if a force is being applied on a body, then definitely the momentum of that body will get changed. Initially, if it was at rest, after application of force on that body, the object will start moving. That means it will gain some velocity. So initial velocity was u and final velocity was v. Mass remains same. But when you are applying the force on that object, as this velocity, that object has gained some momentum, that change in momentum is given by impulse. That means how much change of momentum is taking place in that body, that is the measure of this impulse. Okay, so impulse is measured what is the change of momentum taking place in that object. So which is also given by the product of large force and a small time interval for which force acts on a body. Like you see, when a large force acts on a body on a small interval of time, we say that huge impulsive force is acting there, because impulse is given by F into T, that is force into time. If a large force is acting in a small interval of time, then impulsive force will be also large. So you see, whenever a cricket player, when he tries to catches the ball, right, so he lowers his hand in downward direction, in a backward direction, to increase the time duration. If he increases the time duration, then impulsive force will be less, right, so that he can easily catch the ball. But if he is diving in the front, in a forward direction, then the time will be very less, right, for which the ball may slip from his hand and he may get hurt. So impulsive force can be also written as F into T. Impulsive force can also be written as change in momentum. Okay, so what are the examples for the impulsive force? You see, striking a golf ball with a club, the punch of a boxer on the face of his opponent, collision between a hammer and a nail. So when you are hammering a nail, okay, then it has been seen that a large force is applied in a very short interval of time, so which creates a greater impact. So in the board I have noted down one question. A ball of mass 0.50 kg is thrown with a speed of 10 meter per second. A stationary receives, catches the ball and brings it to rest in 0.02 second. So first we will note down what is given in the question. Mass is given in the question, right? So mass is given 0.50 kg. It is in SI unit. Is thrown with a speed of 10 meter per second and initial velocity is 10 meter per second. A stationary receiver catches the ball. That means when the receiver is taking the ball is coming to rest. That means the final velocity becomes 0 meter per second and brings it to rest in 0.02 second. That means time is also given here, 0.02 second. What we have to find, what is the impulse delivered to the ball? Impulse is given by mv minus mu, or if I take m common, v minus u. What is m here? 0.50, that is 50 by 100. V is 0, final velocity is 0 here. What is u here? You can written as 10. So therefore minus 500 by 100, that is minus 5. Right? So this is the impulse. And you see, what will be the unit then? So we know impulse equals to force into time. You can Newton second you can write here, right? Or you can also write kg meter per second. Okay, so any of the unit you can write here. Now you see, what is the impulse delivered to the ball? Impulse equals to force into time. That means force equals to impulse by time. So what is the impulse here? Just we will take the magnitude and time is 0.02. So 5 into 100 by 2, 250 that means 250 second. Or here 250 Newton, right? By calculating the force here, so 250 Newton. So when we say a force is applied on an object in a very short interval of time, so impulse I equals to F into T. So whenever the force is applied on an object, a large force is applied on an object in a short interval of time, we call it as impulse. So you see, the large force which you are applying on an object in a short interval of time, that large force is compared to what? That is the question arises, okay, when we define the definition for the impulse. Now you see, the force which is being applied on an object in a short interval of time, let us consider that is 0.01 second. The force which you are applying on an object, that force must be greater than any other forces present at there. That means it has to be more than the force of gravity also, you can say, right? Like when a golf is being struck by a club in a short interval of time, the ball is just moving a large distance, it is covering some large distance, right? A large force is applied by a club on the ball. So here we consider this force to be as an impulsive force. So what is an impulsive force? When a large force is applied on an object in a short interval of time, and the force which is being applied on an object is more or greater than any other forces present in at that time. Okay, so this was the impulsive force. Newton's third law of motion. To every action there is an equal and opposite reaction. So whenever you are applying a force on an object, you will receive a force in the opposite direction. Like for example, if we hit a wall, then also we will get an hurt in our hand, right? That means the wall will also exert a equal and opposite force on to you. Like there are very in our daily life we experience this one in a maximum cases. Like when we walk, we find that when we step forward, a frictional force is acting in backward direction. That is, the earth is exerting a force in our foot and we are applying a force towards the earth. That means equal and opposite force acts in this case. So therefore this enables us to walk on the ground. So not only walking, we also see in swimming also. So when we try to move forward, we just move in our hand. So the more force we apply in a forward direction, the more water is being swept in the backward direction, right? So every action has equal and opposite reaction. Like you see, a book is being placed on a table. Let us consider this is one table, right? And the weight of a book is acting in downward direction, and the table is exerting a reaction force in upward direction. So this is an action reaction pair. So that is both the forces are balanced. So this book is in equilibrium. But if you see that the weight of an object is acting in downward direction, right? And if I consider this has to be a table, this is on the ground, right? The earth is applying force on the table, right? And table is exerting force on the book. So when I say action reaction pair, table is exerting force on book and weight of the book is acting in downward direction. So table and book, they are action reaction pair. But if you see the book and the earth, they are not in action reaction pair, because book is resting on the table, its weight is acting on the table, okay? But whereas earth is exerting force on the table, not on the book, okay? So indirectly it is exerting a force on the book, but it is directly it is exerting a force on the table. So this earth and the book is not a action reaction pair, right? So there are many examples which is related to this Newton's third law of motion. So in your screen you can see when we are trying to walk in forward direction, so this reaction force is being resolved into two components, that is, one is r cos theta and one is r sin theta, right? So where r is the reaction force, the force which is exerting, the earth is exerting in upward direction. So when a person walks on a horizontal road, he pushes the ground slanting with one foot, right? This is the action force which is denoted by F. So the ground also exerts an equal and opposite force, so that is given by minus F. That means this ground is exerting a force which is given by R, that is a reaction force which is in opposite direction. So this reaction force is being resolved into two components, that is R sin theta and R cos theta. R sin theta is balanced by the weight of the object, so therefore when we walk we stand still on the ground, but what makes us move forward? This R cos theta. Okay, this component makes us move in forward direction. This R cos theta, when it is more than the frictional force, therefore we move in the forward direction. So in the previous year we had this topic, motion of cart, and we had this, right? So in this time I have not found in the syllabus, so once you check by yourself also whether it is there or not. When I checked that it was not there, right? So for confirmation, just you also see when you go through the syllabus. So motion of a horse, this was missing. So for the motion of the horse, this is very interesting, you see. So let us consider this point to be as horse, right? Its weight is acting in downward direction, and horse is trying to move in a forward direction, so the reaction force is making an angle theta with the ground. This reaction force is being resolved into two components, that is R cos theta and R sin theta. This horse is being tied with a cart with a string, so the force acting on the string or the thread is here, that is T, right? So when it is connected here, when R cos theta becomes greater than the tension, the cart starts moving here. So you see MHA equals to R cos theta minus T. So this was the horse. So it is being tied with a cart, that is with tension, with a string having a tension T, right? So when the foot of a horse is applying or exerting force on the ground is also exerting a reaction force which is making an angle theta with the ground here, as I have told. And the reaction force is being resolved into two component, that is R cos theta and R sin theta. So R sin theta is being balanced by the weight of the horse, and R cos theta component is pulling the horse in the forward direction. Now when an object will move when the forward force is more than the backward force, right? So what is the net force acting on the horse here? You see the net force is given by MHA. We know force equals to MA. So here mass of horse and acceleration. R cos theta must be more than T, then only the horse will move in the forward direction, right? This was one equation, and one equation you will find here for the cart. Now what is the acceleration of the cart? We know net force acting on the cart equals to T is greater than F, where F is the frictional force. So frictional force is between the tire and the ground. So if this tension is more than the frictional force, then only the cart will move, right? So T must be greater than F, and this is equals to net force, right? So what equation we got here? So we can write this acceleration as T minus F by mc, or we can keep this equation as it is, right? So we got here two equations, you see, mca equals to T minus F from first equation here, and from this equation, that is Fh, that means force on horse, that is R cos theta must be greater than T. So Fh can be written as MHA equals to R cos theta minus T. F equals to MA, right? Now if we cross multiply, what we will get here? So if you don't cross multiply, let us consider this equation only, right? So we'll consider this two equation. Now this is equation number 1 and this is equation number 2. If we add equation 1 and 2, that means here adding equation 1 and 2, right? So this equation and this equation was same, so I am just removing this equation here. So this equation, now you see equation number 1 and equation number 2 I am adding. So left hand side and left hand side will be added here, and right hand side and right hand side will be added here. So it has been seen the tension on the string, both are balancing each other. That means how much force is exerting horse on cart, same force is exerting cart on horse. That means both the tensions are equal and opposite, therefore they are cancelling each other. So what we get here? R cos theta minus F, and if I take acceleration common here, what I will get here? R cos theta minus F divided by ms plus mc. So this is the net acceleration which is acting on both cart and horse, right? So this, though this topic it's not being included in the syllabus, but I think few questions might come from here because this is related with Newton's third law of motion.